So as per today's session, we have robot configurations and kinematics. But yesterday afternoon we had there was some technical hitch in the internet connectivity at the end of some centers, so we could not conduct the afternoon session yesterday. So we'll make small changes, although we'll cover the whole content, but we'll have some changes in our program for today and tomorrow. Now I will discuss robot configurations and also discuss briefly the kinematics. Then after tea break, we'll have the session of Professor Pabla on industrial applications of automation. And our afternoon session will be as per schedule. And tomorrow morning, we'll have a special invited lecture on robotics and their industrial applications. That is Mr. Lakshmi Prasad. He works with GI Robotics Bangalore. So he will be discussing some case studies with you. So now we'll begin with robot configurations. Now this presentation, we also covered this presentation in our introductory session. So those slides which we had covered, I may go through them quickly. Now, historical perspective of robots is that the word robot was used first in 1921 by a Czechoslovakian playwright Karel Čapek in his satirical drama titled Rossum's Universal Robots. The word itself is derived from Czech word robota, which means forced labor or slaves. The term robotics was coined by an American author and professor of biochemistry at Boston University. His name was Isaac Asimov, and he also used the term in a short story which he wrote titled Run Around. Then a robot is an industrial robot, which is a mechanical manipulator that can be programmed to perform a variety of tasks, commonly used for welding, material handling, assembly. So in this also what we see is a manipulator, but this manipulator is not programmable. It is operated manually by a person, whereas when we talk of a robot manipulator, that is programmable. So we have robot definitions. As per Webster Dictionary, a robot is an automatic apparatus or device that performs functions ordinarily ascribed to humans or operates with what appears to be almost human intelligence. As per Robotic Institute of America, a robot is a reprogrammable, multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of variety of tasks. So in the technical literature on robots, the second definition is the standard definition. So there are primarily four types of robot configurations. Cartesian, in which we have 3 degrees of freedom and all 3 are linear and at right angles to each other. Second is cylindrical, in which out of the 3 degrees of freedom, 2 are linear and 1 is rotational. In spherical, 1 degree of freedom is linear and 2 degrees are rotational. And in articulated, all the 3 degrees of freedom are rotational. Apart from that, as we saw last time, there is another configuration, special configuration known as SCARA, which also we will see. Now, when we talk of robot configurations, we are talking of only the robot manipulator configurations. We are not talking of the configurations or the degrees of freedom of the tool which is attached at the wrist. In a Cartesian robot, So as per this picture, you can see there are three motions. All the three motions are translational and all the three are at right angles to each other. So a Cartesian coordinate robot, also called linear robot, is an industrial robot whose three principal axes of control are linear and are at right angles to each other. So a popular application of this type of robot is a CNC machine, or generally the robots which are sometimes used with automated storage and retrieval systems. They are also Cartesian robots. So if we see, so here you can see, you will notice that there are three motions and all three are at right angles to each other and linear. Then next we have a cylindrical robot, which is a horizontal arm and it is mounted on a vertical column. This column is then mounted on a rotating base. So we have one rotational degree of freedom because the base can rotate about the vertical axis, and then this arm can slide up and down on the column, so that is a linear degree of freedom, and the arm can also move in and out radially, so that is a third degree of freedom, which is again linear. Sorry. So you will notice here, this was one linear motion, then this up and down is the second linear motion, and third will be the rotation. This is again linear. Then next we have a spherical, also called polar robot. Two rotational degrees of freedom and one linear degree of freedom. So a horizontal arm is mounted on a rotating base and also moves with as the pivot. The horizontal arm can slide horizontally on a repeat. दोबारा करो. वीडियो स्मूथ भी नहीं है, ये तो हमारी बैंडविड्थ इंक्रीज करने पड़ती है.
আসে তো বন্ধ যায়.
Okay, so let us see the video of a polar or a spherical robot. So this is the second rotational, and this is the linear degree of freedom. Let's see it again. It's a small video. So first rotational, again first rotational, second rotational, and then the linear. So next we discuss the selectively compliant robotic arm, that is called SCARA. So it is selectively compliant assembly robot arm or selectively compliant articulated robot arm. Now in the figure, as you see, it has 2 degrees of freedom which are rotational, but the arrangement of the manipulator is such that this end can move only in a horizontal plane, and it has a third degree of freedom which is linear, but it is restricted. It is you can say that's why its name is selective, because it's just only a tool can move somewhat up and down. But this type of robot also has has usefulness in some special applications. So this is a picture of a SCARA robot. The arm is compliant in the XY direction but rigid in the Z direction. Hence the term selective compliant. Right. So as you can see, if we go to the previous, the arm itself cannot move in the Z direction, only the tool can be moved through the Z direction. That is why selective. But in the XY plane, in the horizontal XY plane, the arm can take many positions. The jointed two-link arm layout is similar to human arms, hence the term articulated. This feature allows the arm to extend into confined areas and then retract or fold up out of the way. Let us see a video of this. Oh, I think it's we should use another player because this Nero normally doesn't show this video. Yeah, so I'll use another player. in this video, a SCARA robot transferred 168 parts in 40.99 seconds, that is 0.244 seconds per part. So it shows the speed and the accuracy with which it placed the small steel balls into various slots. Then last is the articulated robot. So here all the 3 degrees of freedom are rotational. So as you can see, there is a base which has a rotational degree of freedom. Then there is a shoulder which again has a rotational degree of freedom. It is this joint and this joint combined, they are also called shoulder joint because they are similar to the human shoulder joint. And then this is the elbow joint. This also has a rotational degree of freedom. So an articulated robot consists of 2 shoulder joints, 1 elbow joint, and then 2 or 3 wrist joints. Example is Puma 560, Motoman, and many more in fact. Let us see a video of.
Have various axis configurations. However, the vast majority of articulated robots feature 6 axes, also called 6 degrees of freedom. 6-axis robots allow for greater flexibility and can perform a wider variety of applications than robots with fewer axes. Axis 1. This axis, located at the robot base, allows the robot to rotate from left to right. This sweeping motion extends the work area to include the area to either side and behind the arm. This axis allows the robot to spin up to a full 180-degree range from the center point. Axis 2. This axis allows the lower arm of the robot to extend forward and backward. It is the axis powering the movement of the entire lower arm. Axis 3. The axis extends the robot's vertical reach. It allows the upper arm to raise and lower. On some articulated models, it allows the upper arm to reach behind the body, further expanding the work envelope. This axis gives the upper arm the better part accessibility. Axis 4. Working in conjunction with the axis 5, this axis aids in the positioning of the end effector and manipulation of the part. Known as the wrist scroll, it rotates the upper arm in a circular motion, moving parts between horizontal to vertical orientations. Axis 5. This axis allows the wrist of the robot arm to tilt up and down. This axis is responsible for the pitch and yaw motion. The pinch or bend motion is up and down, much like opening and closing a box lid. Yaw moves left and right like a door on hinges. Axis 6. This is the wrist of the robot arm. It is responsible for a twisting motion, allowing it to rotate freely in a circular motion, both to position end effectors and to manipulate parts. It is usually capable of more than a 360-degree rotation in either a clockwise or counterclockwise direction. The most popular 6-axis robots are manufactured by Motorman, Fanuc, Panasonic, ABB, and Nachi. To purchase a 6-axis robot, contact RobotWorks at 740-383.
Now, what are the basic components of a robot system? Now in all the videos that we have seen, what we have observed is that a robot, it's basically a manipulator in which there is a movement, rather there are a number of movements in each robot. Now for imparting motion, what we need is, the first thing we need is actuator, and to run the actuator we need a power source. Similarly, to impart the motion to the various parts of robots in a controlled manner, we need a controller along with sensors which will provide the feedback to the controller about the instantaneous positions and speeds of the robot components. So these are the main components. The first thing we need in a robot is a manipulator, that is the mechanical part which will move. And a manipulator consists of series of rigid members called links connected by joints. Then we need actuators which will make the manipulator links and joints to move. To get the feedback about the position, speed, acceleration, torque, etc., we need a variety of sensors, and we need a controller which will coordinate everything. So the controller provides the intelligence to make the manipulator perform in a certain manner. Then we need power conversion units which take signal from the controller and converts it into meaningful power level so that actuators can move. So these are basically driver circuits along with any amplifiers or ADC DAC systems. Now to understand that various components of a robot, let's have a look at this picture. So this picture is of the robot that we have in our laboratory. What you see in this picture is the robot manipulator, a teach pendant, the controller, and the computer on which the software is installed. The teach pendant is used to move the individual links of the robot manually. By manually we mean that when we are not using a program to run it. So on the teach pendant we have a variety of buttons that also we will see. The job of the controller is to make sure that the robot manipulator moves as per the commands. The controller receives the feedback from the variety of sensors installed on the robot, and it gives the command to the motors to move or to stop, and also during movement move at different speeds. Now for programming as well as for a graphical user interface for running the robot, there is interface software which is installed on a PC or a laptop. So using this software we can make the robot move manually, just as we can do the same thing by a teach pendant. So you can say the program is a virtual teach pendant, and also we can make the programs on the or through this interface, and then make the robot follow those program commands in a sequence. Now here we have a diagram for robot arms, links and joints. Now this robot, the name of this model is Scorebot, and what we see is its different components are, it has a base, a body, an upper arm and forearm, and then a tool, which in this case is a gripper. So this forearm is a link, the upper arm is a link, the body is a link, and the base is a link. Whereas on the right hand side we see the different joints. So there is a joint at the base because the robot can rotate about this joint. This shoulder is a joint, elbow is a joint, and this also is a joint which provides the pitch and roll to the robot wrist. So in a previous slide, when we saw manipulator, series of rigid members called links connected by joints. So that is what we are showing here, different links and which are connected by the joints. Then we will see the various actuators and sensors. Now for this particular robot, except for two motors, all the motors are mounted here in the body. So the enlarged view, a photograph from the front is shown here. So here you see a number of motors, precisely 4, 1, 2, 3 and 4 at the back. Now each motor has a gear unit and a sensory unit attached to it. The gear unit is for speed reduction and the sensory unit is for giving the feedback back to the controller about the position and speed of the motor. Then we have timing belts and pulleys attached from which the various joints, using which the various joints can be operated. Now the actuators that you saw in the photograph, they are actually DC servo motors. DC motors because they work on DC supply, servo motors because they provide feedback about the position and speed. So we already discussed that these motors have gear units attached to them and encoder units attached to them. Apart from the encoder units, we also have micro switches attached to the this robot. Now in this side view of the robot arm, what you see is that at each joint there is a cam and then there is a micro switch. A cam and a micro switch. A cam and a micro switch. So when this shoulder joint will move, the cam has its profile is that there is a raised portion around here. So when this raised portion will come here and operate the micro switch, the controller takes it as a reference point that it counts the other positions from this point. So in this image, for example, here the cam profile is somewhat here. So only when this joint will move through some angle, this cam profile will be able to operate this micro switch. So the controller will take that position of the joint as the reference point. Similarly here, the gripper can move like this, which is the pitch of the wrist. So when it moves like this, at some position this profile will operate this micro switch. That will be the reference position for the gripper. Now let us see an actual photograph of this. So for this particular joint, what you see here is the cam, and this cam has a very fine profile in this part. And this is a micro switch, which is basically a spring loaded switch like a doorbell, and this is the button which is to be pressed, and this button will be pressed when the cam comes here. So when this button is pressed, a circuit is complete and the controller gets a signal that the micro switch is operated. Before going to this, as I said that the motors, they also have encoders attached to them. The encoders attached to them. Let us briefly see about the some detail about the encoders. We had seen this proximity switch on Tuesday. We also saw it's working. Now let us see the fundamental about the encoder. So in case of motors, what encoder is essentially a disk which is mounted on the shaft of the motor. So this disk is mounted at the back of the shaft of the motor, and this is the side view of the disk. Now in the side view, what you see is that there is a light source and a photo sensor on two sides of the disk. And this disk has a number of holes. For example, in this view you can see there are 1, 2, 3, 4 holes. Now when the disk is rotating in one complete revolution, the holes will come in between the light source and the photo sensor 4 times. Now whenever a hole is aligned, or you can say collinear, with the light source and the photo sensor, then the light will be able to fall on the photo sensor. Whereas when the hole is not between the light source and the photo sensor, no light will fall from the source on the photo sensor. So when the disk is moving and when there is a hole collinear with the light source and the photo sensor, this photo sensor will give a signal, and this signal is in the form of a pulse. The width of the pulse depending upon the speed at which the disk rotates. If the disk is rotating at a high speed, naturally the width of this pulse will be small. And if the disk is rotating at a slower speed, the width of the pulse will be large, because then the hole will be between the it will be aligned with the light source and the photo sensor for a longer duration of time. Now that means for one complete revolution, for this particular arrangement, we will get 4 pulses, as there are 4 holes in the disk. Now that is about. Now with this type of encoder, what we can do is, by counting the number of pulses, we can determine how many degrees the motor has rotated. For example, if we get 2 pulses, that means the motor has rotated through 90 degree. If a third pulse is also there, then it is 180 degree, and so on. Then also, counting the frequency of the pulses, we can come to know about the speed of the motor. However, to get an idea that whether the motor is rotating in a clockwise or in a counterclockwise direction, 2 pairs of LED and light source and the photo sensors are used. Now in this case, because they are offset, so when the motor is rotating, there will be a lead or lag between the 2 signals, and this phase difference between the 2 signals is used to determine the direction of rotation of the motor. Okay. So as far as the robots are concerned, we use mostly optical encoders in which there is a disk which has a number of holes. In this discussion, I have only talked of 4 holes, but the robot arm that we have in the lab, its encoder has 500 holes along a pitch circle diameter. So that means we can have a resolution of 360 degree by over 500 degrees. Okay, so this we have gone through. Now what is forward kinematics? We'll have a brief introduction to forward and inverse kinematics. Now what you see in the screen is an image in which there is a base and a shoulder, and then there are 2 more joints. This is the elbow joint and this is the wrist joint. Here this gripper is mounted. Now if we see this YZ plane, then we can have a degree of rotation theta 1 at the shoulder joint, a rotation of theta 2 at the elbow joint, and a rotation theta 3 at the wrist joint. The position of the tool in the YZ plane then depends upon the value of theta 1, theta 2 and theta 3. That means if we rotate the three joints through known theta 1, theta 2, theta 3, for example, maybe 60 degrees theta 2, 20 degrees theta, 60 degrees theta 1, theta 2 is 30 degree, theta 3 is 40 degree, then this will occupy a particular position in space. As the angles are varied, its position in the YZ plane will vary. So forward kinematics says that when we are given a set of joint angles, then we find the position and orientation of the tool frame relative to the base frame. So by tool frame we mean to say an XYZ frame that we attach to the tool when we do the computations, and the XYZ frame that we attach to the base. Whereas in case of inverse kinematics it is different. In inverse kinematics it is that, let us say we want to position this tool in space at a particular point, 3D point. Even if we consider a 2D point at this point, say in the YZ plane, we want to position this tool at a particular point, then we need to compute that what should be the angles of different joints so that this tool occupies the desired position in space. Now inverse kinematics is it involves a number of equations, and when we give the command to a robot controller to position the wrist or the end effector or the tool at a particular XYZ coordinates in space, then the controller has to carry out inverse kinematic calculations continuously, because it will do it in steps. And inverse kinematics and for deriving the inverse kinematics in a very efficient manner is a very important thing in robotics, because the whole trajectory through which the robot end effector will move, it involves inverse kinematics as well as calculating the torques that are required to be given to the joint motors. Because remember, the robot has its own mass, so it has its own inertia, so we need a torque to move the joint, and then the requirement will be to move the joint or the link at a certain speed in space. So then also for maintaining particular speed or for providing acceleration to it, we need the calculation of torques. So it's a very complex field. You can find books only on trajectory planning in which only this is discussed, how to compute inverse kinematics, how to compute the torques that are required during a motion. Now for the next 5-10 minutes we'll discuss the forward and inverse kinematics on the board. Deepika. Right. So we will discuss the forward and inverse kinematics. We will discuss the forward and inverse kinematics for very simple cases so as to make the audience understand the concept. Let's say this is an XY. थोड़ा सा फ्रेम बड़ा रखना तो लिखना भी है चाहे फ्रेम बड़ा कर लेना जूम आउट कर देना इतना ठीक है. Let us say this is the XY plane and the origin it coincides with a pivot point on which a single link with a tool is mounted. Now this has only a single degree of freedom as this link can move only in the XY plane, maybe through 180 degree, maybe more than that. So it has only a single degree of freedom. Now, suppose that it is this angle is presently maybe 45 degree or whatever, 60 degree. Then we can easily find that what is the position of the tool in space. By two simple equations, that is x is equal to the length of the link multiplied by cos theta and y is equal to length of the link multiplied by sin theta. So these two equations, they combined, they form the forward kinematics. Because here the joint angle is known to us and we are determining that where will be the end effector in the plane. Now let us say we are told that we require to position this in space at point P, which is maybe 5, 4. In that case, we have to find out the angle which must be maintained so that the end effector is at this position in space. So from these very equations, because here x and y is known to us and the length of the link is fixed, so we know that by these two equations we can calculate the joint angle, and this is inverse kinematics. Now if we consider this single link, the end point of the single link can move through. This is the locus of the end point of the link. So that means this particular link, a tool can only move through a line which is a curve in the XY plane. So a single link is not much useful. So let us extend our further. Now let us say we have two links. The length of this is L1 and length of this is L2. So this angle is theta 1, and for the second also we may define the angle with reference to the x-axis or with reference to the previous link. Normally in robotics, the angle of a link is defined, is referenced with reference to the previous link. So for this angle will be theta 2 will be with reference to the previous link. Just for making that simply in a diagram, let me remake the diagram. So now we have say two links. Now with two links, this tool can move in the space, but it can now occupy a number of positions because it can now rotate about this joint also. So we have a very good flexibility. The reach of the tool now becomes quite large. So now in this case, the X position in forward kinematics, the X position will be determined by L1 cos theta 1, L2 cos of theta 1 plus theta 2. Similarly, Y will be given by L1 sin theta 1 plus L2 sin of theta 1 plus theta. Because this angle and this angle will be same. Now in this case, if we are given that we want to position the wrist at say 10 and 7, then accordingly you can see from this equation, now we can rewrite the same equations, but just in the other order. Now x and y is known to us, L1 and L2 are fixed. So therefore, we have two equations and two unknowns, that is theta 1 and theta 2. So using these equations, we can then calculate what is theta 1 and theta 2. But again, this is a very simplified, uh, you can say two-link planar manipulator. This has now two degrees of freedom. One is theta 1, the second is theta 2. So that means it is like our arm which can move only in the plane. So the shoulder angle is theta 1 and the elbow angle is theta 2. But as we know, we can also move in the third direction. So when that is added, again these equations will become now complex. Okay. So we will have a third degree of freedom also, so which will make inverse kinematics really complex when it has to be calculated in milliseconds by the controller. So that is the fundamental about forward and inverse kinematics. Actually, Professor Corrine Kalra was to discuss this in detail for various type of robots, but he had to go out. So in his place, we have invited Mr. Lakshmi Prasad from JA Robotics. Mr. Prasad may discuss an overall configuration of robots and their applications, but he may not go into kinematics details. So I have given you a glimpse of what is forward kinematics, what is inverse kinematics. So I will go to it. Now let us discuss something about robot programming. Let me just go through this. Let me open another presentation because I want to discuss something more in detail. Okay. So robot programming, it serves as interface between human user and industrial robot. So as we just discussed, it is used for describing the desired locations of the operational point or tool center point relative to a user specified coordinate system. Now we always want the robot rest to be at a particular XYZ point coordinates in space. For example, if the robot is going to do a spot welding operation on automobiles in an assembly line, then we know that at which points the spot weld is to be made. So those points are measured in space, and then accordingly they are given to the robot in the program. Now the desired positions of the TCP are recorded in teach mode. So that's what we are saying, that how do we know that what is XYZ in space. So what is done, that an automobile body will be placed in front of the robot, and then using the teach pendant the robot arm will be moved manually by the operator, and he will take the robot wrist to the desired XYZ point in space, record that position, then he will orient the tool to the desired orientation, record that position, and those points will be then used in the program. So teach mode is when we are moving the robot using teach pendant. Actually, because this lecture is through Google Hangout, so we are using the laptop of the studio. So I have the details about the teach pendant in my laptop, so I'll bring it, and in the afternoon session we'll have time on that also. So the desired positions of the tool center point are recorded in the teach mode. That is when the robot is moved manually by the person using teach pendant. So after these points are recorded, then a program is made in which these points are mentioned, and then the program is executed in run mode. So these are some standard programming language which were used earlier, but nowadays when you buy a robot, it has an interface software with it, and they have always made a set of commands. The supplier always provides you a set of commands for that particular robot, using which you can easily program it. Right? So let us see a robot program. We also saw it briefly in the introductory lecture, but let us discuss it in detail. Now this program is about a pick and place operation. Since the object is to be picked from one location and placed at another location, so what are the requirements? That positions are to be taught in the teach mode, that is manually, and recorded. Then speed of the robot is to be decided based on inertia and distance. After recording positions and deciding speeds, program is coded using relevant commands. And then the program is executed, resulting in the robot performing required operations. Now what you see here is the interface for the scoreboard robot that we have in our lab. So in this you can see it's basically a program having a title bar, a menu bar, a tool bar, and then there are a number of windows. Now this is the window for writing programs, and this is the second window in which various commands are available to us. At the left bottom of the screen what you see is two more windows. So this is for the left window is for making the robot move in the teach mode, and the right one is, and this window is to record the positions. So as I said, we can either move the robot through the physical teach pendant that is supplied with the robot, or through the window on the in the program. Now, how do we make a program? So from the set of commands that are provided by the supplier, we will select a particular command. For example, here this a go to position command has been selected. So when we select this command from here, a window will appear in which we will specify which position the uh, robot has to go to, and then we have to specify whether we are referring to a joint or the wrist. So in this particular case, we are referring to joint. Then we have to specify the speed at which speed it should be moved. I think in the next slide you will see a close-up of this window. Right. So this is a close-up of that window. So as you can see, we are saying go to position, target position 1. So this was a joint joint angle that were recorded, and we are saying that it's a joint. Then speed. In this particular software, we have three options. Either we can simply say fast, then the robot will move, that particular joint will move at the highest possible speed, or we can say give a speed range from 1 to 9. 1 corresponds to the lowest and 9 corresponds to the highest. So in this example, we have specified a medium speed, that is 5. Or the third option is duration. We can specify that we want this position to be reached from the current position in this much time. Then the controller will decide at which speed I should move the joint. So after we specify the uh, position and the speed, then that command is automatically written here. So here you can, maybe you are able to read or not, but it's written go to position 1 speed 5. And then it is ready to take the second command, so which we will select from here, specify the positions and speeds, and that command will also appear here. So in the second command, an open gripper command was given, then a third command, then the fourth command, which has yet to come here. So we have selected a wait command, and one by one the commands are added and a whole program is made. If you look at this side here, now you see a large number of commands, whereas in case of previous there were smaller commands. That is because you can expand a particular group of commands. So here the groups have not been expanded. In the next year the groups have been expanded. So this is a complete program. Now this is the same program written here for the convenience of the audience so that they can easily read it. So in this you see the first command is go to position 1 speed 5. Next is open gripper. Third is go to position 2 speed 1. Then next is wait command. Close gripper. Again go to position 1 speed 1. Then go to position 3 speed 5. Then go to position 4 speed 1. Then wait open gripper, go to position 3 speed 1 close gripper, wait 3 seconds, then go to position 1 speed 5. So you will notice that in this program basically we are talking of 4 positions, 1, 2, 3 and 4. So before we further discuss this program in detail and see the video, let us discuss this program on the board so as to better understand what is position 1, 2, 3, 4. So this program is about a taking a object from one location and placing it at a second. Say this is one location of the object, the initial position, and the target is here. That is the object must come here. Now we will have the robot gripper. Let us say initially the robot gripper is at its home position. When we have to start the program. Now what we want is we have to do two things. Move the gripper, open the gripper, close the gripper. These are the basic three things we have to do. So normally uh, what we do is we move the grip, move the wrist, the tool with the gripper closed. So first we must move the gripper to a point which is just above this. Say this is the point 1 where the tool comes, position 1, where the tool comes with the gripper closed. Now from here to here we can move the tool at a higher speed. But once we are here, then we must open the gripper and then move the tool at a lower speed. So after we give the command, this means whatever is the current position of the tool, it will go to position 1 at a medium speed. Now here we want the gripper to open. So we give the second command. When we do this, the gripper will open. Now we want it to move slowly to which position? To this position, where it can, where the gripper fingers are around the object. So after this, we opening the gripper, we say and we want the movement from position 1 to position 2 at a slow speed. So that is why now speed is 1. Once it is here, then we would like to close the gripper. When we give this command, these grippers will grasp the object. Now this object is to be placed here. We cannot slide it along the surface. We must clear the object from the surface. So what we do is we want the tool to move back to position 1, which is slightly above. So again position 1, but because it is holding an object, maybe at a slow speed. So when we give this command, the tool will come to position 1 with the object grasped. Now we want it to move from here to somewhere here above the surface point. Not too high, but we would like that when this comes here, it is quite close to the surface, but the object should not strike the surface. Maybe a few millimeter above the surface. And we have already recorded these positions, remember, by manually making the robot. So from here, then we will give a command because it has to move through empty space. We can give a higher speed. So when we give this command, it will move here. Now from here, we would like it to be lowered very slowly so that the object is just placed on the surface. So when we give the next command, our fourth position is that the object is now placed on the surface. So then we will say open gripper to release the object. The grippers will be opened, and after that we would like the tool to move up so that grippers are clear of the object. That means we would like to go back to position 3. With a slow speed. So once the empty tool is back to here, we may close the gripper, we may not close the gripper. So we can again send back to position 1 and the whole cycle will be repeated. So the program is repeated in cycles and the robot will keep on picking the object from one place and keeping it at the second. So naturally we are assuming that objects are coming here. It is constantly placing them here. From here they are being taken somewhere else. In case the objects are to be picked and stacked, then we have to very clearly increment the coordinates. We will record one position initially, and then in the program only we will increment the coordinates so that the objects are stacked. So let us now go to the laptop. Okay. So I just wrote the whole program on the board except for some wait commands that I did not write. So they are only to give a waiting to the robot. So you can see the video for this now. So this is position 1, position 2 actually. First it will goes to, now this is position 1. Now open gripper. Now there is a wait command. Then position 2. Close gripper. Again back to position 1. Position 3. Position 4. Release. Back to position 3. Now again to position 1. So the program has again started. So the program is now running in cycles. Okay. Right. So that is about the how we can make the robot programs. Now, any questions from the centers? Gyan Jyoti,
Hello.
hello, I'm Dr. Neeraj.
Yes, sir.
Good
Sir,
morning.
I want to ask a question.
Uh-huh.
Sir, what is the configuration used in spot welding?
What is the?
What is the configuration of robotic arm used in spot welding machines? Spot welding.
Okay. You see, it will depend that where the object on which the spot welds are to be made, that is, how much are they approachable. So if say there is a kind of a flat surface on which spot welds are to be made, then we can have a simple Cartesian type robot.
Okay.
But if, for example, in a car body, the robot wrist, maybe you have seen on the TV itself, there are a number of times they show such things on the TV. Even in the news, it's a very common picture that you see in the news at a assembly line of a car and a robot doing spot welds. So in case the robot wrist has to be moved, maneuvered through certain curves, and then we will have to we will need at the most 6 or 7 degree of freedoms.
Okay.
So it all depends upon the process.
Yes.
Of course, we would like that for a given process we go in for a robot which is simplest, because that will also be economically more feasible, and a simpler configuration also moves, the maintenance is also less, and there are less chances of errors creeping in.
Sir, which configuration has the most flexibility and reachability? In terms
Articulated.
of. Okay.
Articulated.
Okay, sir.
You
Thank
see,
you, sir.
you can yourself see that our arms are fully articulated manipulators,
Yes, sir.
and they can reach infinite points within the workspace. That if you extend your arm fully and move it in all the possible directions with fully extended, that is a workspace.
Yes, sir.
Even then, you don't have all the points where your hand can reach within that workspace. For example, maybe some parts of your back. So
Yes,
those points are called, you can say they're called normally uh, not null. There's a particular term for that. I'm just forgetting. So within a workspace also, the robot rest may not be able to reach, but fully articulated robots are most versatile.
Okay, sir. Thank you, sir.
Okay, welcome. Any other question?
Not from our centers.
Okay, from Punjab University Regional Center, Sharpur.
No, sir, we do not get any question.
Okay, madam, thank you. 8, Odisha.
Hello, sir.
Yes, please.
Good morning. I am CS Patra from Gate, Barampur, Odisha.
Yes, sir.
You are told Kara robot. It is a fine designing process because when we are in Graphite India, in Bensam, we had used same like this processor. Two guide ways with two bearings supporting horizontal arm is mounted on two vertical columns, sir.
Okay.
Another thing, sir, as per timer setting to the timer belt and the bar size will be cut automatically as per the size. The timer belt will be, we have to set it as per the size of the bar, sir. So this is the process. As you told in Scala robot, it is very similar to that one. Because previously it was automatic, not automatic. It is
Yes,
manual,
yes, yes.
operated manually, sir.
Yeah, yeah.
We did it automatically, sir. By hydraulic system, adding hydraulic system and pneumatic system, it is
Right,
a,
right.
it is a grand success, sir. Eh?
That's right. That's right.
So
That's
when I had your Scala robot, I recall all these things. Thank you for this good
it,
suggestion.
right. It is nice to hear your experience.
Yes, sir. Thank you, sir.
Right. Thank you so much. Thank
Okay, sir. Thank you. Bye.
you. SCS VMB University, Tamil Nadu. There are any questions? SCS VMB University. Sir, I think your mic is maybe mute because we are not able to
Yeah,
listen to
yeah,
you. Yeah, now
yeah,
it is okay.
yeah. Sir, is there any? Hello?
Hello. Yeah,
Sir,
please speak.
yeah. Sir, if the robot is moving through the piston, right?
Through the
Piston movement, right? So if the viscosity of the fluid is changing,
uh-huh.
will it affect the speed of the movement of the hand, sir?
You are saying that if the robot is moving a piston,
Yeah. Through the piston only the hands are moving, right?
okay. Well, what I get from your question is that
If the fluid
if
is
the
heating,
yeah, that's what I'm saying. That if the robot rest or the tool is moving through a fluid,
yeah,
then you are saying that whether the forces acting will vary.
yeah, yeah, yeah.
Yeah, naturally, because you see, the forces will depend upon the aerodynamics also, the viscosity, everything. So the forces will vary and the speed will also then vary. So in that case, if we have given asked the controller to move the tool at a given speed, at a constant speed, then the controller will recompute the torques and accordingly try to keep the tool speed or velocity as close to desired as possible.
Okay, sir. Thank you.
Okay, thank you. So any questions from the participants in the studio? Okay, so then we'll thank you very much. So then we'll break for tea. It is I think 11:25. So we'll reassemble a gate at 11:45 for the next session by Professor Pablo on industrial applications of automation. चाय ले लीजिए। दीपक को आया कि नहीं चाय वाला? आ गया? ओके, चलो मेरे को पता नहीं। चलो आगे चलो। लेके आया जी, मुझे पता नहीं कैसे आया।
इसका पोजीशन हमारे ऐसा ਉਹਨੂੰ ਕਿੱਦਾਂ ਪਤਾ ਲੱਗੂ ਉਹਨੂੰ ਪਹਿਲਾਂ ਦੇਣਾ ਪਊਗਾ ਐਕਸਟਰਾ
हाँ पहला हम
यानी कि रेफरेंस एक बार
देख
देना
के बंदा देख के आया ਨੂੰ ਬੂਟ ਕਰਾਈਦਾ तो चाहे लगे भी है ठीक है उन्हें रिपोर्ट कर दे।
आगे दीपिका अरे आगे बस यहीं से बोल दो
सारे हुए थे
पता करता हूँ okay very good morning to all of you participants with me in the studio and participants at the centers. I am Professor Pabla. I am Professor in Mechanical Engineering at this institute. So I have been asked to talk to you on industrial applications of robots. By now you are fairly familiar with what robots are, and I am very sure that you will be knowing what are the applications. So I will just be refreshing what you already know. Now let's say where robots will be used. Robots are basically a part of automation of industrial working. How it has come? We used to have manual automation. Now it is basically completely automated systems. Otherwise, we had semi-automatic systems where partly the job was done by the operator and partly it was done by the system. You can take the example of a conveyor, belt conveyor or a roller conveyor. Here you just keep the component on the conveyor just by gravity because you have a slope, you have a slant in the conveyor, and the component rolls down to the next position. In the direction of automation in manufacturing, flexible manufacturing systems was an major break. Of course, CNC machines came, which automated the manufacturing systems, manufacturing of the components. But as a system, automation in the manufacturing system, FMS was a major break where you integrate many systems. You integrate many machines. You have, let's say, 8-10 machines, or you have more than 2 machines, or more than one machine. You integrate it. Integrate it with the help of what? Integrate with the help of a material handling system, a conveyor system, or a robot. You have a integrating computer system which controls all the machines and the material handling system, and the system becomes autonomous. They become autonomous systems where you have to just provide the material. Rest of the things are taken care of the control system and the equipment in the manufacturing system. That means a robot will load the component on a machine. When the machine is sure that the component is loaded, properly loaded on the machine, a robot will go away from the machine, it will withdraw, and the machine will start working on the component. It will start machining. After that, when the component is machined, the machine stops, a robot comes again, holds the component, machine declamps the component from the fixture, and the robot takes away the machined component, and in turn it loads the second component on the machine. So it was a almost complete automation, and it was integrated automation without very little human interference. Now these are few terms which will be used in robotics. You must have already been through this. Artificial intelligence involves the use of machines, computers, and industrial robots to to replace human intelligence. That means artificial intelligence is that you program human-like intelligence into the machines, right? Expert systems, of course, they are also intelligent programs to perform tasks and solve difficult real-life situations. Expert systems can tell you what medicine you should take based on the symptoms you give to the computer. You say, I have such thing. This system will say that, okay, you take one paracetamol. Now, based on the inputs, it can give the diagnosis, it can do the diagnosis, and it can prescribe the solution also. It can give the solution also. Now, I have just given the one example of medicine prescription, but let's say you have a machine which is not working, which has stopped working. Now, the system can ask you, you have an expert system for maintenance of that machine. It will ask you some questions. That, okay, if this is happening, this is happening, this is happening, then you check such and such V-belt. It is there. Has it not broken? So you take action accordingly. Let's see what are the applications. Where do we use robots? It is a common thing. We have been talking that we will need robots where we want to replace human workers. Why do we want to replace human workers? Maybe there is a hazardous environment, chemicals hai, na, painting booth hai, nuclear installations hai, where the environment is harmful to the human being. So what you do is you put a robot there. Let the robot do it. What is a robot? How it works? You already know by now. Okay. So we try to replace the human beings from the tasks which are harmful to the human being, which are not to the liking of the human being, which may be dirty work. Right? I don't want to do it. No human beings want to do it. But I can put a robot there. There are repetitive tasks which become boring for the human being. And when the task is repetitive, you start making some mistakes somewhere. But this robot will not do. Why? Because robot has been programmed that, okay, you first do this, then do this, then do this, then do this. उसके लिए तो 3-4 टास्क हमने बनाए हुए हैं. That, okay, first pick the component, then travel to one place, drop the component. Okay, first place the component there, open the gripper, come back to the original position or some other position. So that repetitive tasks we have programmed, and the robot will work as per the program. Whereas we are working as per our memory, and we try to sometimes bypass the things also. Right? Boring and unpleasant tasks, I said I don't like a task, so I want that I should automate it. Right? Because a robot has a computer, inbuilt computer, or it is connected to a computer which remembers the things. A robot doesn't do anything by itself. It has to be told to do something. It has to be programmed to do something. Right? Robots are basically, most of the time, they will be reprogrammable. Right? That you program it to do something. After that, the job is finished. Then similar things, maybe within a limited domain, you can reprogram the computer, the robot, to do another job. But similar things, maybe it may not be universal robots, that it can do anything and everything. But similar jobs within a limited domain, it can work. Multi-shift operations. Humans get tired. Right? Human beings get tired, but robots will not. Robots may fail. Component may fail after repetitive loading and unloading. Fatigue loading हो सकती है. peak failure हो सकती है, but they don't get tired. If something has failed, let's say robot fails, we can redesign it and we can have a better robot which will never fail. But human beings will keep failing. And because it is a programmable thing, it is a machine dependent thing, the performance over a period of time remains the same. It has been observed that human beings, when start working in the morning, let's say 9 o'clock, efficiency is very good. Around 11 o'clock, 12 o'clock, they get tired, they break for tea, the efficiency has gone down. Then after lunch, probably they start feeling sleepy, they are lazy, the laziness comes, and the efficiency comes down. But that thing will not come in machines and robots. Their performance will be consistent. Right? When you have consistent performance, what will happen? That means I can predict how much I will produce in a particular period of time. कि 8 घंटे में मैं 100 component बनाना है अगर मेरे planned है and planning is okay, then I will get 100 components in 8 hours when the machine is working. But when human beings are working, maybe you may not be very sure, there can be slips. Where there are infrequent changeovers. Now we talk of intelligent robots also, that they can adjust to the situation. But if there are not intelligent robots, they will keep doing whatever you want, whatever you have programmed. If some obstruction comes in between, let's say workplace and the target, the robot will not stop. It will hit that obstruction. But in intelligent robots, where you have vision systems, vision sensors and all, maybe it can take care of that also. Performing at a steady pace, I told you that they will keep repeating at the cycle time will remain same. Operating for long hours without rest. Responding in automated operations. Minimizing variation. Quality is another issue. Let's say you are doing some assembly operation. A robot will do the same assembly again and again. Especially, let's say, in electronics components, where components are very small. And you are likely to miss some of the components while assembling. Operator is likely to miss. But computer will not miss. Robot will not miss. So, when you are using robots, there will be variation will be minimal. Variation will be minimal. Now, industrial applications of robots can be divided into material handling operations. Biggest thing which robots have done is material handling applications. Now, what is material handling operation? Involve the movement of material or parts from one location to another location. It includes parts placement, palletizing and or depalletizing, machine loading and unloading. Now, let us see. Involves movement of materials or parts from one location to another location. That means you have to pick and place. Pick and place means the robot may move. It is not that the robot is stationary and it is just picking and placing. The robot will pick the component, move to a pre-programmed path and leave the component at a different place. There is something called ASRS, Automated Storage and Retrieval Systems. That means there is a robot which, when the new material comes, you give the part number and location, robot will pick up the component and store it at a particular place. And the computer remembers where a particular component is stored. At the same time, when you want to retrieve that component, when you want to withdraw that component from the store, you just tell the computer, you just give a command that I want such and such component. The robot will go to a particular location, pick up the component and give it to you at the desired location. Robot can be used for shifting the material, heavy material, material which is not suitable to be picked by the human being. So robots can be made to pay. The only thing is we have to design the robot for that particular application. What does the design of the computer, this robot involves? How many degrees of freedom you want in that robot? कितने movements चाहिए आपको? Do you want the robot to move or it should be stationary only? What type of work you want it to do? Because depending upon the type of work you want the robot to do, you have to design the system. What is the weight it wants to carry? What is the weight you want the robot to carry? Depending upon the weight you want the robot to carry, you have to design your complete system. इसमें मशीन डिजाइन आ जाएगा आपका, मटेरियल डिजाइन, मटेरियल सिलेक्शन आ जाएगी, स्ट्रेंथ आ जाएगी सारी. ऐसा ना हो ना कि रोबोट का हमने डिजाइन तो कर लिया इधर तो घूमने के लिए, बट रोबोट की उसकी कैपेसिटी नहीं है कि उसको उठा ले, उसकी मोटर की पावर उतनी नहीं है कंपोनेंट के वेट को उठा ले, उसकी लिंक्स जो है मैकेनिज्म जो पूरी आपने बनाई है उतनी स्ट्रांग नहीं है कि उसको उठा ले और टूट जाएंगी बीच में. So you have to design the robot accordingly. It should have required strength, it should have required degrees of freedom, it should have required tooling. Tooling means if it is to hold something, it should have a proper gripper. It has to, let's say it can be made to do welding, then it should be able to hold a welding torch, right? It has to do, it can do painting for you, but then it should have the facilities to hold the paintbrush or spray gun, whatever you want. Once you know what a robot can do, applications will come automatically, right? We are talking about industrial applications. It involves part placement. Part placement means, as I said, you pick up and place at a particular place. Machine loading, that okay, you pick up the part and put it on the chuck of the machine or table of the machine where holding fixture is there. So what will happen? What all is involved in this? Next, robot ने तो component उठाया और लगा दिया. Now it has to be ensured that the component goes into the proper location. अगर आपने proper location में component नहीं लगाया तो क्या होगा? उसकी machining proper नहीं होगी. If you are not machining properly, that means you will not get the finished component which you want. It will be a rejected component. That means you have to ensure that the component is placed at the proper location. How do you ensure? That means you should have some sensing system. You should have some sensors, depending on what you want to do. As soon as you keep the component into the fixture or in the chuck should close. Now, chuck should not start closing before the component is inserted into the chuck. And it should not start closing before the component has gone into the chuck. That means I should have some sensing arrangement which tell the control system that okay, now the component is placed properly. Now clamp. Once the clamping has been done, the robot should leave the component. But then it should get a signal. The robot should get a signal that the clamping has been done now. That is, the component is properly held into the clamp, and then robot should leave the component, right? Then the robot should retract. Robot should retract. Now, while retracting also, it should not hit the component again. We have to plan accordingly. In material handling system, normally there are two types of robots you can use. One is, let's say there is a system where you have a conveyor between the machines. The components being transferred from one machine to another machine with the help of a conveyor. Or let's say you have a storage space and you have a robot which brings the components from the storage space to the machine and it stores it there. There can be two material handling systems. One is primary material handling system, which is connecting the machines and the storage space. It can be a, let's say, conveyor belt. You have a conveyor belt or a roller conveyor, on which the components are kept and brought to the machines, right? Then you can have a small robot at each machine, or serving to particular number of more than one machines, which picks the components from the conveyor and keeps in a small storage which is at each machine. Let's say you have machines. Let's say you have 2 machines. At each machine, you have small storage space, so that you can keep some working process at each machine, so that the machines are not starved of the fresh material, raw material. So from that small storage, what we call it a buffer at the machine, you can have a robo which picks the component from the buffer and places on the loads on the machine, right? So that becomes the secondary material handling system. Now, but these have to be integrated with machine tool. A secondary material handling system which is serving the machines, which is putting the material from the conveyor to the buffer storage, from buffer storage to the machine, from machine to the finished goods storage. It has to interface with the machine, one, that is, it has to be interfaced with the machine, that the component will be loaded only when the machine is not working. When the component is loaded, the machine should clamp it. When the component is clamped, the robot should withdraw. Maybe it should pick the next component, or it can be used for the other machine. Robot can load the other machine. When the component is machined, the robot should it should get a signal and it should go to that machine and hold that component when the machine stops. Now there has to be a lot of interlocking in this. That when the machine has stopped, only then the robot should go there. When the robot has clamped the component, when the robot has gripper has a hold on the component, then the chuck should open. When the chuck is open, then the robot should move out. All that has to be interlocked. So it is not a simple thing. We have to understand the total control system. How does it happen? It is not that difficult. You can have a PLC system to control all this. You of course need sensors for getting the inputs. Pelletizing. What is pelletizing or depelletizing? Pelletizing means, let's say you want to put the let's say you have boxes, you want to store it on a pellet. Pellet मतलब फट्टा जैसे होता है, ठीक है? या बॉक्स में रखने आपने. You have some components which you want to store in a particular pellet. How will it work? कैसे काम करेगा? रोबोट कैसे रख देगा अलग अलग जगह पे? Let's say I have a small flat plate on which I want to put 10 components. I don't want to put one component over the other component. I want to put side by side. So robot will work basically on the coordinates. That okay, I have put one component at such and such coordinates, next component will be on such and such coordinates. So it will go to that coordinate system, x and y coordinates, x, y and z coordinates. All things will work on location only, coordinates only. We have to give the coordinates. If I want that it should go and place the component there, I have to give the location. Location in terms of x, y, z, right? That is the only solution. Or you have some sensors that okay, when it senses a signal from this, it should stop. When it stops, the gripper should open. When gripper has reached some particular distance, it should close. The gripper can have sensors in the gripper itself. Let's say, many times I ask this question, that if you want to pick an egg with the robot, what type of sensor you have? What type of end effector you will have? I want to pick an egg. The size of egg can vary, right? Location of egg can vary, where it is lying in the particular space. So what is my requirement? Irrespective of the size of the egg, I want to pick it up. I want to pick the egg. I want to have enough pressure holding power on the egg so that it doesn't slip from the gripper. At the same time, I should not have so much of pressure on the egg that it breaks. So I need to have some sensors, type sensors, force sensor, maybe somewhere vision sensor also, if I want to locate it also. So depending on what you want, you need to have a sensing system. Once you understand this, it is all simple after that, right? Pelletizing and depelletizing. That means putting it somewhere in the pellet, as well as depelletizing means removing it also. From, let's say you have a big box in which there are 10 boxes. You want to pick one box which is at this height. After that, the next box is, let's say, at this height now. We have to tell the robot that, okay, the next box is deeper than the first box by this much length, so that it knows where it has to go. Otherwise, अगर आप वही जगह पे फिर आ जाएगा robot यहाँ पे आके पकड़ने की कोशिश करेगा, it will try to find something, but this box is already been removed. आप कोका कोला के क्रेट की देखिए जिसमें वो सेव करते हैं. If I want to fill it with the help of that crate, जो that plastic storage box जो है जिसमें कोका कोला, let's say Coke bottles आती हैं. Now there are 12 bottles, but location of each is different. I cannot tell the robot that, okay, go to this position and same position every time. No. If it goes to the same position again and again, it will throw the bottle on the bottle. But I want that it should fill the bottles in the plastic storage place, so that one bottle comes in the one slot. So I have to give the slots that, okay, first go to this, then increment this location by this, then increment the location by this, right? I can put it in a loop that, okay, do 6 times this, then thoda sa niche aa jao, again 6 times, right? 24 bottles agar maine rakhni hai to I have to give the coordinates, right? It all works on coordinates and some other sensors which will sense. Let's say you want to have a system. Let's say, coming to the same thing, Coke bottles only. Let's say you want to have an automatic filling machine there. So the bottle will come to a particular place, right? When the bottle comes below that nozzle from where it is to be filled, the system should sense that the bottle is at the proper place. Then something from nozzle from the top should come and fill the material into the bottle. When it is filled, either by liquid level or by weight, you sense it. कि जब इसका weight इतना हो गया bottle के साथ या liquid का level यहाँ तक पहुँच गया, the flow should stop, the nozzle should retract, and the bottle should go ahead, isn't it? So that is the system. That is the system robots are also following. So material handling applications will include both primary and secondary material handling, palletizing, depalletizing, machine loading, machine unloading, right? Moving the material also, storage and retrieval of the material from the storage, automated storage and retrieval. Just think of it. Anyway, those who are sitting here, we have a system here now. we have just purchased, that we have our ASRS system, that they should go and visit that lab. It is under installation. Now these are material handling operations. Then you have processing operations where you can use robots. What are the processing operations? It requires the robot to manipulate a special process tool as the end effector. In fact, I have told you earlier that you, depending upon what application you want, you need an end effector. You want an end effector for doing that job. You want to do soldering. So you need a soldering rod at the end of the robot, and you need something in the robot end effector which can hold the holding rod. Right? The applications include spot welding, arc welding, riveting, spray painting, machining, metal cutting, deburring, polishing. Any operation actually where human being can do, it can also do. The only thing is we need to have a suitable instrumentation, suitable tooling for that. Right? It can do spot welding. It can do better than human beings do. Because human beings can have different judgments. I can have different judgment, you can have different judgment. But robot once programmed, if I say that, okay, do spot welding in a particular grid at particular points which are, let's say, 100 millimeters away from each other, it will go exactly. Once you have initialized it in the initial first position, उसके बाद exact 100 millimeters पे ही होंगे वो सारे. Because the system is so good. System accuracy is very good. So it can do all these applications. Spot welding, arc welding, riveting, spray painting. Just see. First figure is this. On the left, material handling. The robot is handling the boxes. It can be made to stack the boxes one above the other. Just see this application. If the robot has kept one box has already been kept there, the next location, either the robot should have the capability that it should judge where is the box lying, already the box lying, what is the position, उसके ऊपर ही रखना. दूसरा तरीका क्या है कि हमें पता है कि इस पहले बॉक्स की हाइट इतनी है, उतनी हाइट पे तो चला गया, तो नेक्स्ट हाइट है उसके ऊपर आना चाहिए बॉक्स. सो वी गिव के फर्स्ट बॉक्स तो हमने ग्राउंड लेवल पे लगाया, उसके बाद जो 500 मिलीमीटर ऊपर है उसके ऊपर तो दूसरा बॉक्स है 500 मिलीमीटर के ऊपर आएगा. But if you don't want to do it, you have an intelligent robot with more sensors, more sensing elements, more complicated systems, where the system will decide where is the vacant place. Kitni height isko already jani hai. But then you should have instrumentation for that in the robot and as well as in the environment also. Then next is the assembly robot, where you can assemble the components. Basically, mostly in electronics, it should be very useful. Where the components are small in size, large in number, and people forget sometimes. You see, in electronics, if you forget to put one component in the system is going to fail. When a human being is doing, there are methods to make it fail safe, that means foolproof. But in computers, in robots, what happens? It is programmed and it repeats. There is no chance of leaving any component because repeatability is so good. Then this Kawasaki robot which is shown, this is a skill for welding. Now, spot welding करवा लो, let's say arc welding करवा लो, straight line पे welding करवा लो, gas welding करवा लो. The only thing is you should have proper end effector which should hold the tooling, and it has to be guided by a program. Then assembly application, major area we have said. involves part handling manipulations of a special tools and other automatic tasks and operations. There may be some situations where you want a particular component to be in a particular position so that it can assemble with the other part, meeting part. One is that you ensure that the component will be placed in a particular position only. है ना? अगर square hole है square उसका साथ ही मिलना चाहिए, ऐसे घूम के नहीं, अगर if you rotate that component, meeting component, तो उसमें जाएगा नहीं वो. But robot can do it with the help of computer. It can sense the location and it can correct the location. It can correct the orientation. Robots can be used for inspection operations. Now, inspection requires the robot to position a work part to an inspection device. That means one is that, okay, the robot will be used only in putting the component on the inspection device. Inspection device will do the inspection and robot will pick up the component. Right? So, inspection component and inspection system is different. What is the role of the robot is that it is just placing it in the proper place. When inspection is complete, it is picking it up. But it is interfaced with the inspection equipment so that it places it in the proper place, and when the inspection is complete, it gets a signal from the inspection equipment and it removes the component from the inspection equipment. Second is, one is that, okay, you pick and place the component on the inspection machine. When inspection is complete, remove it. Second is, the robot is doing some measurements also. Involve the robot to manipulate a device or sensor to perform the inspection. You can make a robot take measurements. I don't know whether there is something like called CMM. CMM is also a CNC machine. Robot is also a CNC machine. Basically, what we are doing, we are manipulating the motions. Then we are sensing some more things. So you can ask the robot that, okay, you have a probe in the robot which can touch different places. Depending upon where it is touching, how much has been the movement, you can see what is the dimension. You can make a robot trace a profile and check the profile of the component. एक कंपोनेंट के ऊपर आपने एक प्रोब से उससे ट्रेस करवा दिया कंपोनेंट को, वही ट्रेस that robot जो सॉफ्टवेयर आ गया इंस्पेक्शन सॉफ्टवेयर, robot will not do that. Those points which are picked, those will be passed to the inspection software and it can tell you, okay, what is the profile of this. Or if you wanted, let's say, a radius of 25 millimeters, whether it is 25 or not, it can tell. It can take touching at 3 points and tell you the arc of the radius of the arc. We have done it. If you see, part placement, palletizing, depalletizing, machine loading, unloading, stacking and insertion operations. So, robot must have the following features to facilitate material handling. Manipulator must be able to lift the parts safely. The robot must have the needed reach. Reach means it should be able to reach that component. We say this is a work volume, right? The robot controller must have a large enough memory to store all the programmed points so that the robot can move from one location to another location. This is not an issue these days. Computers have fairly large RAM and otherwise memory also for storing it. Robot must have the speed necessary for meeting the transfer cycle of the operation. That is very important. If I want to produce some component, let's say I want to pick and place that every 2 minutes I should place a component at a particular plate. The robot should have the required speed, that it should be able to accomplish that cycle time. It should not delay my working otherwise. My other machines may be fast, but robot has to be equally fast so that my cycle time is not delayed. My production rate is not reduced. So I need to match the speed of the robot with the requirement I have. transfer requirements. Similarly, we are repeating it. Part placement. The basic operation in this category is the relatively simple pick and place operations. This application needs a low technology robot of the cylindrical coordinate system. Only 2, 3 or 4 joints are required. Pneumatically powered robots are often used. Palletizing. Requires robot to stack parts one on top of the other, that is to palletize them, or to unstack parts by removing from the top one by one, that is depalletizing them. We have discussed this. This also we have discussed. I can again read. Robots transfers parts into and or from the production machine. There are 3 possible cases. Machine loading, in which the robot loads parts onto the production machine, but the parts are unloaded by some other means. That means a press working operation where the robots feed the sheet blanks into the press, but the finished parts drop out of the press by way of gravity. Machine loading, in which the raw materials are fed into the machine without robot assistance. The robot unloads the parts from the machine assisted by vision or no vision. Machine loading and unloading, that involves both loading and unloading of the work parts by the robot. The robot loads the raw work into the process and unloads the finished component, that we have discussed. Stacking operations we discussed. Processing operations. Robot performs the processing procedure on the part. The robot is equipped with some type of process tooling as its end effector. Manipulates the tooling relative to the working part during the cycle. We discussed all this. I have explained to you. Spot welding, continuous welding, spray painting, metal cutting and deburring operations. Various machining operations like drilling, grinding, laser, water jet cutting and riveting, rotating and spindle operations, and adhesive and sealant dispensing. That means you want to apply adhesive at some place, give that adhesive to the robot moves and applies the adhesive uniformly on a particular surface. So this is arc welding. If you see, there are two here there are 2 work tables. Just see where this man is standing. On one work table, the robot is working. On the other work table, on the left side towards me, there is a component which has been loaded by the worker, operator. So what happens? The robot is working on one component, and the operator has loaded another component on the work table, second work table. As soon as the robot finishes welding on the first part on which it is already working, the robot shifts the welding to the second part. The operator will unload the welded parts and put a new workpiece there. The robot will finish the working on the left side component, and after finishing it will go to the, by that time the operator would have loaded the next component on the right hand side table. So robot will immediately start working. It is a question of saving time. Or traditionally labor-intensive activities in industry and are highly repetitive and boring, hence are logical candidates for robotic applications. Inspection operations, we have done. Some inspection operations require parts to be manipulated, and other applications require that an inspection tool be manipulated. Inspection work requires high precision and patience, and human judgment is often needed to determine whether a product is within quality specification or not. That can be done by the computer now. Once you have given the specification that I want only 25 millimeter diameter with this much deviation, if anything is coming out of that deviation, robot can inspect it and it can segregate also. Let's say I have given the limits that I have a shaft where the diameter should be 25 plus minus 0.1. That means the diameter should go from 24.99 to 25.1 millimeter, right? So robot can be interfaced with the inspection equipment. It can measure the diameter, and depending upon the diameter which is coming from a particular component, if it is within this range, it can allow it to go to the next station. If it is out of this range, let's say 25.2 आ गया किसी का diameter, the robot can pick up that component and place it into the eject bin. right? Just see. Inspection tasks that are performed by individual robots can usually be divided into following three techniques. By using a feeler gauge or a linear displacement transducer known as LVDT, the parts being measured will come in physical contact with the instrument or by means of air pressure, which will cause it to ride above the surface being measured. By utilizing robotic vision, matrix video cameras are used. This has come actually now. Scanning, nothing to do with robotics, but 3D scanners are there now. You just put your component on the table in front of the scanner. The scanner will scan the component and give you the inspection report for particular dimensions, variables. That okay, these are the dimensions which are out of control. The robots may be active or in passive role. The active role robot is responsible for determining whether the part is good or bad. In passive role, the robot feeds a gauging system with the part. पहले में तो क्या है, एक्टिव में क्या है, robot will decide also. I said if it is beyond the limits, acceptable limits, it will say okay, rejected. जो पैसिव रोल है रोबोट का उसमें है कि ओके इंस्पेक्शन करके डाटा इंस्पेक्शन वाले को भेज दिया, उसके बाद कोई एक्शन नहीं लेगा. It will not tell it rejected or rejected. That decision can be taken afterwards somewhere. Now, these were some of the applications. Of course, one of the major applications of robotics is coming in medical sciences. Robots are doing heart operations, bypass surgeries. Robots are doing stitching, human body stitching after operation. Robots are doing scanning. Very big area of robotics application is now medical applications. Now, how do we evaluate the potential of a robot? Evaluation of the potential of a robot depends on analysis of the application, long and short term application. Because robots, putting robots into action will involve some cost. We have to decide whether we should go for robotics applications or not. Should we continue with manual work or some other work, or should we put a robot? Should we put a robot for machine loading, unloading? Yeah, operator karta hai, theek hai. So for that, these are some guidelines. It says analysis of the application, long and short term objectives, manufacturing and processes involved, what type of manufacturing is involved, space availability, budget, and system objectives. Feasibility study. How a more automated system will affect related operation in the plant. हमने तो रोबोट तो लगाया, ऑटोमेट कर दिया, बाकी ऑपरेशंस का क्या होगा जहां पे रोबोट नहीं लगा? Are they feasible? Are they compatible with this? Material handling methods, commercial equipment available, CAD cell simulation. System proposal, functional specifications, system operations, robot type. That means we have to decide robot type, tooling, peripheral equipment क्या क्या उसमें चाहिए होगी. So this is just so in case that this last part is when you have decided to go for a robot application, what you should do. It says it should make the functional specifications of the system. What do you want? क्या क्या करना उसने, क्या क्या काम करने हैं. क्योंकि जो भी आप robot खरीदोगे, वो what applications you want to put the robot to, that will decide. What type of anti-factor will you have? How many degrees of freedom you will have? What should be the strength of the links, arms of the robot? सिस्टम ऑपरेशन कैसे होगा, रोबोट कैसे होगा, टाइप डिग्रीज ऑफ फ्रीडम, टूलिंग क्या क्या चाहिए उसके लिए, वेल्डिंग करनी है, असेंबली करनी है, इंस्पेक्शन करनी है, क्या करना है, पेरिफेरल इक्विपमेंट और उसके लिए और क्या क्या चाहिए. अकेला रोबोट लगाने से कुछ नहीं होगा. मे बी इट नीड्स सम मोर इक्विपमेंट टू बी इंटीग्रेटेड इनटू द सिस्टम. Okay, we will not go into this. A future application is medical applications of the robots, routine examinations, surgical procedures, underwater applications, involves in prospecting for minerals on the floor of the ocean, salvaging of sunken vessels, mobile firefighters to be used by Air Force and Navy, surveillance and guard duty. Border पे surveillance करनी है. Robots can walk. अभी तो हमारे फौजी करते हैं, BSF वाले करते हैं. Robot can walk and do security duties, and they will not get tired also. They will not get killed also, and they will give continuous data. आजकल तो क्या हो गया that you have a, let's say, robot moving, you are getting real time data. Robot is at, let's say, on Pakistan border. You are sitting in Delhi. आपको डाटा दिल्ली में आता रहेगा. आजकल तो इंटरनेट सिस्टम हो गए हैं सारे. These are some of the grippers. Depending upon what type of application you have assembly application, you have welding application, you have holding pick and place, you have arc welding, you have spot welding. What type of application you have, that type of gripper you must have, and the system complicacy will also depend on what is your application. So these are few of the applications I want to discuss with you. Dr. Dhami told me to finish by 1:45. I am in time. Any questions you have? चलें? Okay. ज्ञान ज्योति. ज्ञान ज्योति. Very good afternoon.
Good afternoon, sir.
Good afternoon.
Sir, no question from our side, Gyanjyoti College.
Okay, thank you. Thank you. SCS VMB University, Tamil Nadu, Kachipuram. Very good afternoon.
Hey, you are saying many application and so on.
Yes, sir.
Nowadays, there are a lot of job cuts are happening in the industry.
Let us talk about robots, not about the social scenario.
No. I'm not talking about that one.
Yeah.
But anyhow, because of the installation of the robot in the industry, only the problem in this. So how can we tackle this situation and so on?
You see, when robots will come, there will be different type of jobs will come. My idea was that we will talk only about the applications of robots. You are talking about something else. When CNC machines came, people thought there will be a lot of unemployment due to CNC machines. But when there is one CNC machine, you have one operator, we have one programmer. When earlier only one person was handling the maintenance of CNC machine, now you need a person from computer science, you need a computer from electronics, you need a person from electrical, you need a person from mechanical. So job opportunities will expand, and there will be value addition to the jobs also. People have to be trained in those areas.
What are the areas we can take up?
Yes, sir. Yes, sir. We are not getting you. We go to the next center. Gate.
No question, sir. Clear.
Hello.
Hello.
Yes, sir.
Thank you, sir. No question.
Thank you. Thank you. This is which center? This is a Punjab University. Okay.
Good afternoon, sir.
Very good afternoon.
Here is question from our side. As robots are supposed to do many operations in industry like spot welding and wave soldering, etc., where there are temperature ranges very high. A normal robot is supposed to work in extreme temperature conditions or only in controlled temperature conditions so far?
No, you can select your materials depending upon what you want. Depending on the application, you have the that should be taken care at the design level of the robot itself. So because let's say there is a welding operation, how do you control the temperature there?
We can't.
It has to work in the normal working environment itself. What time, madam, nikal gaya hai when CNC machines were operating in air conditioning?
Yes, sir.
Yeah. So it has to work in the normal environment only.
Okay. Thank you so much, sir.
Okay. Thank you. Okay, then thank you very much. Thank you for listening, and we will meet at 2 o'clock again. Thank you.
Okay, good afternoon. So in this session, we will discuss introduction to control. But before that, in the हाँ जी ਇਹਦੇ ਵਿੱਚ ਹੈ ਉਸ ਤੋਂ ਵੀ ਕਰ ਸਕਦੇ ਕਿ ਨਹੀਂ ਕੰਮ Center is connected. Okay, no fans. अपने फैन नहीं चलने अपने. अच्छा कल वही है. Okay, good afternoon. So there is a lot of renovation going on in this block, due to which the generator supply is not available in all the rooms. So there was a power failure, that is why you had to wait. So in this session we will discuss about fundamental of controls, but before that a few things, like for example teach pendant, which I wanted to show in the morning, but unfortunately at that time the slides were not with me. So we have around 6-7 slides for the teach pendant, and then we'll come to our main title of this session. I think we'll have to wait. The PPT is not starting. Maybe we are installing something. PPT is starting already. So please wait for 5 minutes. We are installing a software, and in the meantime the PPT is not starting. Okay, so they will switch to PPT. Okay, so some slides which were not there in the morning with me. So what you see here is the scoreboard robot with the arm fully stretched in the horizontal plane, and from the top view, if we see on the right hand side is the work envelope, top view, right? So this is the arm fully stretched, and the arm can move in the plane up to this angle. It is 330 degree through which the arm can move. Similarly, this is the side view. So in the side view, this is the work envelope. So combining these two views, we can get an idea of the work volume of this particular robot. So this slide was also not there with me. So here we have a detailed drawing of the sensors, encoders rather, which are installed on the motors of this particular robot. So this shaft that you see, this is the shaft So this is the shaft of the motor, right? On one end of the motor, as we saw in the morning, are the gears. On the back side, the encoder is installed on the shaft. So the encoder has a disc consisting of a number of holes, and what we see here is very small printed circuit board on which two pairs of LED and phototransistors are mounted. And the assembly of the LED phototransistors and the disc is encased in a plastic cover. So as the motor shaft rotates, the disc also rotates, and from the signals of the phototransistor, the speed and velocity as well as the direction of rotation of the motor is determined. This is a close-up view of the micro switch that we were talking in the morning. The micro switches which are operated by the cam to determine the reference point of the joint positions. So this is the switch, and this is the button which gets depressed by the cam when the cam rotates. Now this is the close-up view of the controller. This is the front view and the top view. And the back view. In the back view, what you see is that this is the connector through which all the motors and sensors of the on the robot manipulator are connected to this controller. This is the USB cable which goes to the computer, and this is the cable from the teach pendant. So this is a close-up view of the teach pendant. So if you see that it has an LCD display, then there is a button which can be set to auto mode or to teach mode. There is a second button for emergency stop, and then there are a number of buttons for operating individual joints and other commands. Now the button is right now set in the auto direction. If we set it to uh, if we set it to teach, then we can work with the teach pendant. But if we set it to auto, then the robot has to be controlled through the software. So this we saw in the morning. There is again a photo. Okay, now here you see, here it's a close-up view when the knob on the teach pendant is in the teach mode, and maybe I don't know if it is visible, but it displays a message teach pendant in teach mode. Whereas if the knob is set to auto mode, it shows that teach pendant in the auto mode. So when the teach pendant is in control, the software control
आएगी सर फिर से टू आएगी जरूर फिर से टू
Center सारे connected हैं. Okay. Okay. So we have we're getting a frequent power breakdown. That is why there is slight delay. डेस्कटॉप ਦੇ ਫੋਲਡਰ ਕਿੱਥੋਂ ਆਉਂਦੇ ਆ ਡੈਸਕਟॉप ਉੱਪਰ ਆ ਨਹੀਂ ਰਹੇ थे अच्छा फेवरेट है ओके ठीक है Okay, so we'll resume. In the meantime, when the power is stored, maybe there'll be another break in the session for 2-3 minutes. Okay. So when the teach pendant is in control, the software is disabled, and when the software is in control, the teach pendant is disabled. Now this is a close-up view of the commands available on teach pendant. So you can see there is a button on which 3 options are there: joints, XYZ tool. Then there are more buttons on which number 1, 2, 3 or axis 1, axis 2, axis 3 or XYZ is written. So if we want to move the robot joint wise, we select the joint option, and then if we press this one, then the first joint, which in this case is the base joint, that will be moved. When we press plus or minus, similarly if we select 2, then the second joint, that is the shoulder joint, will move when we press plus and minus accordingly. Or if we select the XYZ mode, then we can specify X, Y and Z coordinates for the tool in the workspace, and then the controller will itself perform the inverse kinematics to determine the joint angles through which the joints must be set in order to achieve that particular XYZ. So we can have joint axis 1, axis 2, axis 3 rotations for the tool, wrist pitch and wrist roll, and for gripper jaw, gripper open close, homing, XYZ motions. Okay. So that was just an overview of teach pendant that I wanted to share with you. Now we start with this session on control. That is fundamental of control. We'll also demonstrate on a small kit tomorrow morning. Okay. Now for that, let us see a dynamic physical model, a standard mechanical model showing the inertia M, the damping D, and stiffness K. Similarly, in electrical engineering, we can have a model consisting of inductance, resistance, and capacitance. Now, if a force acts on the mass, a displacement will be produced. The mathematical model for this is given by the standard equation m d2x dt square plus d dx dt plus kx is equal to f, where f is a force function of time, small x is the displacement, and dx dt is velocity, and d2x dt square is acceleration. Now we can also write this differential equation in terms of Laplace transforms, whereby dx dt is represented by s into x, where s is the complex variable, and d2x dt square is represented by s square x. Now when we write a differential equation in Laplace form, then basically we convert this into an algebraic equation. So therefore we can take x as common term. So we can write the mathematical model as ms square plus ds plus k into x is equal to f. Then we normally write x is equal to this. Why? Because in the system we are considering force as the input and x as the output. So this ratio is called then the transfer function, because it correlates the output to the output to the input. So with force as the input and x as the output, we have the transfer function 1 over ms square plus ds plus k. Now this we can also represent in terms of a block diagram, where the block represents the transfer function, force is the input to the system, and x is the output. Now a very important thing to see here is that ms square plus ds, these are the terms which involve the derivatives. So these terms will have an effect as long as x is varying. When x becomes constant, the derivative of x will become 0, and the second derivative will also become 0. So in that case, that is the steady state when displacement is constant, and the effect of inertia and damping will be nil. So at that time, f will be equal to x will be equal to 1 by k into f. Now, when we talk of control, we are basically referring to that we get an output from a system that we want. For example, in a room, if you want the temperature to remain 19 degrees centigrade, then the control system's job is to measure the instantaneous temperature in the room and then provide cooling so that the temperature remains 19 degrees centigrade. Similarly, if you are talking of a motor, if we want a motor to run at say 2100 rpm, then the job of the control system is to get a feedback from the sensors about the current speed of the motor and make sure that the motor runs at the same speed even if the load is being increased or decreased. Now, for this particular example, it is fairly simple that if we want x to be, let us say, 10 centimeter and the value of k is known to us, then we can very easily calculate what will be f, because f will be simply k into x. So if we give that f, then we'll get the x. However, this thing will be applicable only on the steady state. The transient behavior of the system will depend upon these two terms, that is ms square plus ds. So even though we may be able to calculate manually that what input should be given to a system for obtaining a particular desired state, still the transient system has to be controlled also. because we may want sometimes that okay, the overshoot should not be more than this percentage, or the response of the system should be fast, like that. So basically what we do is, for us the system remains this only, where the input is capital F and output is X. So we usually use controllers which will give the control action to the system so that some desired output is obtained. Now, what information do we supply to the controller? That information in this case will be difference between the desired value of displacement and the actual value of the displacement. So this difference, which is called error signal, this is provided by measuring the instantaneous displacement, providing it to the controller, and punching in the controller the value of X that you desire. For example, a very simple example is microwave oven. So when we start microwave oven, we specify a time that whether we want to run it for 30 seconds, 40 seconds, 1 minute, etc. So that is a reference input. And the output is the actual time which has elapsed since the microwave oven was started. So when the actual time becomes equal to the reference time, then the oven will stop. So here also, then what we do is we basically make a system in which to the controller we provide the error signal, that is what is the desired displacement and what is the actual displacement. The actual displacement or the reference displacement will be given to the controller by punching its value through the keyboard of the controller, and the instantaneous displacement will be measured by some sensor. So these two will be compared. The error signal is applied to the controller, and the controller then decide, okay, what force should be given to the system so that desired output is obtained. So that's how we get basically a closed loop control system. Now we'll use MATLAB now to simulate these systems so as to get a better idea of that how does a controller work, and also what is a PID control, because here we have taken PID control in this example. PID stands for proportional integral derivative, and this type of controller is most common industrial controller. Okay. Let me. So what we see right now on the screen is the open loop system for this mass damper spring example. So say we give it an input force of 1. So what will be the displacement? So if it is 1 unit, then X will be something which will depend upon the values of M, D and K. Leaving aside values of M and D, if K is equal to 1, X will be 1 only. If K is equal to 2, X will be 0.5, because X will be always F upon K at steady state. So the values of M and D will decide the transient behavior of the system. So let us simulate it by taking the value of M as say 1 kg, damping as 1 Newton second per meter, and stiffness as 1 Newton per meter. And force we have already specified as 1 Newton. So I'll just specify these values at MATLAB prompt. Let me increase the font size. say we give m as 1, d also as 1, and k also as 1. So with m as 1, d as 1, and k as 1, the steady state value of x will be f by k. Since f is also 1, k is 1, so x will also be 1. So we run the simulation, and then we see the displacement. It will be shown in the form of a plot. Okay. So on this plot, on the x-axis we have the time, on y-axis is the displacement. So as you can see, at about 10 seconds, the displacement settles to a value of 1, and up to that point, the transient behavior of the system is this. So we may run the simulation, let us say for longer duration, say 20 seconds, so as to okay. So now on the x-axis we have time from 0 to 20 second, and on y-axis again the displacement. So what we can see is that at about 10 second, the system obtains, rather about 9 seconds, the system obtains a steady state value of 1, whereas up to that point we have the transient behavior. So if we say increase the damping or decrease the damping from 1 to 0.5 and then run the simulation, so then what should we expect? A change in the transient behavior. Right? The steady state will remain same, 1 only, but it will come late now. So the transient behavior will be for a longer duration, the overshoots will be more, the number of oscillation will be more. Whereas if we increase the damping, say earlier initially it was 1, we make it 1.5, and then run the simulation. So now you can see that the damping has the oscillations have decreased from both the previous cases. Okay. So that means if m and d is known to us, then we can decide the value of k so that we can calculate what should be f for x. But actually the systems are not that simple. In actual working condition, a lot of disturbances are there which we may or may not be able to anticipate. So we cannot determine the coefficients we cannot determine the input so that we get the desired output. That is why the closed loop control systems are used. So that even if in case of any unwanted or you can say foreseen disturbance, we get the desired output. Okay, so let us now simulate So what you see now screen is both the models, the first one which we just simulated along with the second one. Now here we have inserted a controller, and in this controller I have set the value of three parameters as proportional equal to 1, integral 0, derivative 0. So that means effectively it is a proportional control only with a proportionality constant 1. So if the proportionality constant is 1, that simply means that f is equal to the error signal. That is the difference between what is desired and what is actual. So with the given values of m, d and k, let us reset our values to initial ones. That is m is already 1, k is already 1. So we'll set d also equal to 1. That is our original value. Now we simulate this. Just a minute. I'll leave this. Okay. So now we have desired reference as 1. Now this is displacement. Here the input was force, whereas here this input is decided by the controller. So here this is what we want. Okay. So open loop response you have already seen. Right. This is the previous one only. The first one. This is the second one. Now in this case, it is actually bad response as compared to the open loop response, in both in terms of steady state as well as transient. Steady state it is bad because the final output is 0.5, half of what we require, and bad in terms of transient also because the oscillations are more as compared to the open loop response. Right. So this is because when we put the system in a closed loop, the mathematics of the whole system changes. Right. So keeping that in view, we have to decide the parameters of the controller, or we may have to incorporate some compensators. So just to indicate the effect of proportional, integral and derivative, now let me show that we set the proportional, increase the proportional control from 1 to 2. Now again the steady state response is somewhat improved. Now it is nearer to 0.7, whereas we want is 1. The desired value is 1, but the transient is bad. So going by this, let us try to increase the proportional control to 10 and see what happens. So with this, the steady state response does go up. It is still not 1, but the transient becomes very bad. Now, as we could see, howsoever we may increase the proportionality constant, the output will never become equal to what is desired, because that can be checked by mathematical computations also, which we will not do here of course, but it's quite elaborate. So what we'll do is we'll take our proportionality constant to 1 back. Now we will introduce the integral constant, which we have put as 1. Now we will run the simulation. Let us run for a longer duration of time because we are not able to see the actual steady state. So now we see that the output at the steady state does reach equal to 1, which was desired, but the oscillations have become very large. So what I said was that the proportionality constant coefficient, or you can say the proportional controller, will not be able to give us the desired steady state value howsoever we may increase it. There will always be some error, howsoever small it may be. So the steady state error can be controlled by integral control. We can rather offset the steady state error to 0 by integral control, but that is now increasing the oscillations because overall the control has increased. So without following any scientific methods, Deepika, so without following any scientific methods, I'm just doing hit and trial. I set the derivative value to 1 to see that what is the effect of derivative. Right. So now you will see that with derivative, the oscillations have decreased. We'll again see with only proportional control, we have this kind of response. The steady state value is 0.5, whereas the desired is 1. And there is an overshoot. If we incorporate integral control, then the output value reaches 1, that is the desired value, but the oscillations increase very much and the steady state is reached quite late. Whereas if we incorporate derivative also, then what we see that the derivative control has an effect on the transient behavior. The output remains 1 only. So the basic role of integral control action is to remove the steady state error, whereas the role of derivative control action is to improve the transient behavior to you can say damp the oscillations. So any question up to this point? So we are just discussing the fundamental of control systems. So if there is any query from the centers are connected. Okay. गेट भी है कि नहीं गेट okay. So any query from the participants in the studio?
Hello, sir.
Yes, please.
This is SCSVM University.
Yeah.
I want to know about how the diagram which is shown in earlier. Which software you are using that to draw the diagrams?
I am using Simulink, MATLAB Simulink.
Simulink.
MATLAB.
Okay.
I am using MATLAB and Simulink.
Okay.
Yeah.
Sir, can you once again show the demo?
Sure.
Yeah. How to draw the diagrams and also.
Okay, fine. So you want to know how these diagrams were drawn, right?
Yes.
I'll show it now. Okay, so I had brought this model ready-made, so I can show you how these are made. So basically, this is the interface of MATLAB, and you can start Simulink, which can be used to make block diagrams from the button available. So I have already opened the Simulink. So when you will open Simulink, Simulink library browser will open. Now to draw a block diagram, right, we click on new model. So on the toolbar, or there will be menu bar also. So you get a blank file. Now in this particular example, I was using the transfer function blocks. So Simulink has quite a good number of libraries, and transfer function block is available in the continuous library. So here we have a transfer function block. So you just click the mouse button and drag and drop it on the blank file. I will increase the size. Let me draw. Now what we need is that, because by default when you draw a transfer function, let me enlarge it. It will always show like this: 1 over s plus 1. I was using a mass damper spring system, so I was showing 1 upon ms square plus ds plus k. So that we can do by specifying the coefficients of the numerator and the denominator. To do that, you double click on the block, and a function block parameters dialog box will open. Here you can specify the numerator coefficients and the denominator coefficients. The default coefficients for numerator is 1, for denominator it is 1, 1. It's a vector of 1, 1. Now in the denominator, if I write, let us say 1 space 2, and I say OK, so you will see here it changes to s plus 2. So basically we provide the coefficients in there. Now if I change the coefficients to 3 space 2, then this will become 3s plus 2. So we are specifying coefficients of the polynomial in the denominator. So if you have a transfer function like s square plus s plus 1, then you have to specify 3 coefficients: coefficient of s square, then coefficient of s, then coefficient of 1. To be more, just to distinguish, the first one will always be the coefficient of the highest degree term of the polynomial. So now this will be s square plus 2s plus 1. Then we have to, for the open loop system, we can choose a block which corresponds to a type of input that you want to specify. So we have two libraries. One is called source. In source, different types of inputs are available. Example, step, ramp, sinusoidal, pulse, a number of types. You can also make your own signal. So if I give a, say, a step type, then we can drag and drop the step block. Then on every block, input and output ports are shown. So you connect the blocks by connecting the input output blocks. So here we have a transfer function 1 over s square plus 2s plus 1, and there is a step input to it. For the output, if you want to display it in a scope, then from the sync library you can choose different types of outputs. So scope is the most common, which is basically oscilloscope. So now our model is complete. So we have given an input to the system, and then there is the output can be seen here. You can change the time period from here for which you want to run the simulation. Also, you can change the time at which the step change should occur. You can specify what was the initial value of the signal, what is the final value, etc. And then you run the simulation, and then you view the simulation results by double clicking on the scope. So it shows this kind of response. Obviously, because I had given a quotient of 2 with S, that means the damping is quite high. So if I had given this as 1, that means lesser damping. So then the response will be different. So that is how you make the blocks, block diagrams. If you want to make a feedback loop, then you have to incorporate other blocks. For example, there is a block called sum. So by default it has 2 plus signs, but just by double clicking we can change the signs. So now we have a comparator. You can have a block here for, say, a controller. So PID controllers will be available in Simulink Extras. Let me see if it is there. Okay. So in earlier versions they were in Simulink Extras. I think now they have changed. Okay, it used to be an additional linear, but I can just tell you after checking that in which, because right now on this system which belongs to ETV Studio, which is used to relay the lectures, I have installed only basic MATLAB and basic Simulink. Otherwise there are nearly 80 toolboxes, so all have not been installed because of shortage of space and time. So in earlier versions of MATLAB, the PID control was available in Simulink Extras. So here I will just check and let you know tomorrow. So that is how you make the block diagrams, and then you run the simulation. There's any other question you may ask? But it is a good tool to be used not only for research but also for classroom teaching also. Okay. So whatever effects we have shown you through simulation, tomorrow we'll show it to you through a small kit. Right. That kit consists of a DC motor, and so we'll show that how a P or I or D control, what is the effect of them on the position control of the DC motor. So tomorrow we'll have 2 sessions in the morning only. So the course will be over by 12:45 before lunch. So at 10 o'clock first we'll have session by Mr. Lakshmi Prasad, who is from GI Robotics Bangalore. He will discuss with you some case studies of robots and some latest sensors that are used in automation. For example, now for keeping track of components on assembly lines in the industry, RFIDs are used, and so many other things. And then we'll have a demonstration on PID control on a physical hardware. So if there are any questions, you are most welcome. Otherwise, we'll break for the day. Have any questions? Okay, great. Okay, thank you very much. So we'll meet tomorrow morning at 10 o'clock. Attendance.